Hi, I'm here. Can you hear me? Yeah. I need to turn down this just background music that I have playing for a second. Hi, you are currently on air, so don't say anything that you don't want recorded. Yeah. Well, you're on my stream because I'm testing it. So, yeah, click on that link. Yeah. Yeah, you're gonna hear everything I say like 10 seconds later, so you're gonna want to mute that stream. How do you mute anything in YouTube? Yeah, there you go. See, Socratic method. It's the way to teach. Okay. No, that's, the college sent me these pictures for backgrounds in Zoom. And I was like, I'm totally gonna use them, so... Okay, so this is what I want you to test. So I'm going to hit a button, and the screen should change, and it might take a second. No, it'll totally change. Yeah. Okay, yeah. And then I'm going to type something in the chat box, so... It takes a second. It's a little slow. Yeah, so, like... It is feeding through my computer and I'm recording that. No, I connect into YouTube. Right, so it goes into the chat. It's like 30 seconds or so. It was working okay last night, so... Okay, and then I want to click on this one. I actually got to bring up PowerPoint, or not PowerPoint, but, so, let me see here, so... That's just Photoshop. Yeah. I have a tablet and a pen. Did it actually print Hi Brandon for you? Okay, cool. That's really everything I have. Yeah, like, I think it's all set. Okay. That's really all I wanted to know. I have a preview here, and I have a preview of what shows on YouTube, but I don't know if I trust it. Just because, like, yeah, it looks great on my end, but what about, like, somebody who is not involved with my end of things at all? Okay. Okay, cool. Yeah, as long as everything's working, that's all I need. Remember, you're live. You're live. I sort of just had to do this when I could do it. I'm just doing both, yeah. It archives them, and the test stream I did yesterday is still there, so I'm happy. Yep, which is the whole point. They just can't chat with me in live time if they're watching the archive, but they send me an email, that's fine. Yeah, that's because it's live. Well, there aren't any in there. There aren't any students currently connected, because the lecture doesn't start for 20 minutes. I haven't posted the link. I mean, I guess I could just, like, stop the stream or something. Like, I can hit a... Yeah, I guess I could do that, huh? Well, there are 2 people watching. Yeah, Brandon teaches at Edmonds Community College, and he's doing the same stuff that we're dealing with right now, because that is every college everywhere. So, yeah, collaboration. Tell your friends. I might actually need that. I have to rework my labs because I'm obviously not making my students do a lab book. I'm gonna make a bunch of worksheets, and I gotta figure out a way to make Google Drive work so I can like have people upload data into that. Don't say the word extra credit on my stream. Don't say extra credit. Those words are forbidden. Let's work on the regular credit first. Yeah. Yeah. Okay. So I might talk to you about that. That seems a little bit too much for a first quarter class. Like, that's a 6th quarter class that you're doing. Oh, I mean making a video. But yeah, like, I could just have them put papers in there and then download them. That's totally fine. Yeah. I mean, that's fair. Okay, I'm gonna hang up on this call because I gotta post my link. And, yeah. Okay, good luck. We're all counting on you. Oops, I didn't unmute my mic. Hopefully everyone can hear me. Let me hit the magic button. Boop. The chat should be on the screen now. I don't really need this window open. So I'm going to do this so I can still see you, everybody. I got to do this, and hopefully everything doesn't close. Alright, welcome to Chemistry 161. My name is Wes Hillman. If you weren't here for the test stream yesterday, I am happy to be here. A little nervous that I'm actually doing the thing I'm supposed to be doing instead of playing a video game, because this is actually a little easier for me, but it's more prone to mistakes. Oh, I do need the screen up, actually. At times, we're going to go into a view that looks kind of like this, and presumably I should be able to draw all over the screen. I just have to Alt-Tab to that. Where is my... There it is. Oops, that's not what I want. Hold on. I didn't actually hit the thing. There we go. That's... Why am I not writing? I already have technical difficulties. This is great. Hold on just a second. I want red. This should be drawing. I don't know why... Oh, I might not have selected anything. There we go. So that's working. Okay. So, oops, that doesn't work. Let me clear this away. Give me just a second, actually. I need to do something really quickly. Alright, there we go. So we should be good to go. Alright. There are going to be a few technical issues that pop up now and then. I am going to be constantly clicking back and forth between windows, so if I accidentally hit a button and it does something unexpected, like it goes like this or something like that, that's just because I'm fumbling with the keys, because I am a big oaf. But for the most part, this is how our lectures are going to be presented. We are going to go through the slides one or two at a time. I'm going to talk a little bit about the content on each of them, and hopefully you will be taking some sort of notes. Don't just sit there and listen is my advice for you, because the content will go pretty quickly. I will try and address questions as I see them. You are more than welcome to use the chat for whatever purpose you want to, but if you have a question specifically for me, I would ask that you preface it with something like, I don't know, like this, question for you, whatever, and like have like a symbol or something like that, so that I know, like, hey, this is a question that I want you to answer, and not just like general chat, because I'm going to try and be parsing this as I talk to you. Alright, so without further ado, let's get started. The first section of Chemistry 161 is all about the essentials of chemistry, basic understandings of like what matter is, how we can sort it into different categories, and then what we do to measure properties of matter. So like what mathematical tools do we have at our disposal? So we're going to go through a bunch of that today. We're going to see how far we get in 2 hours. After 1 hour, I will take a break. My clock is not on the screen because my PowerPoint is in front of it, so I will just get my phone here. All right, here we go. So what exactly is chemistry? You're enrolled in this class for a specific reason, and for a lot of you, it's going to be because, hey, it's a prerequisite. My understanding is that at our college, we have very few chemistry majors. The reason for that is because chemistry is a very foundational science, but not a lot of people want to just do chemistry, which is a shame because chemistry is awesome. Chemistry is very important for biology. It's also very important for materials science, so if you're going into engineering, you need to have a good, strong background in chemistry. But what exactly is this field? Like, what are we studying? It turns out that people have been asking that question for a very, very, very long time. So, since the dawn of civilization, people have asked, like, what is this stuff and what can I do with it? And they had a bunch of ideas on what they could do. and they had a bunch of ideas on what all of the things around them were constituted from. So, for instance, a long time ago, the Greek civilization decided, I guess we'll say, or postulated, that all matter in the universe was constituted from basic elements, and those four elements were fire, air, earth, and water. You know, the Final Fantasy elements that you use fire on things that are weak against water, and so on and so forth. There was a fifth element that wasn't discovered until a long time later. That's Lilu. Haha. Hopefully you've seen the Fifth Element. I realize that movie might be older than a lot of you. Um, but for the most part, in ancient times, people didn't really have any idea. They were just kind of guessing, like, what are the elements that make up the world around us? Air seems pretty obvious. Fire must come from the sun. Yeah, multipass. There you go. That's the important part of that picture there. Many years later, so I think this is around like 1200, 1580 on the screen here. During some of the golden ages and Renaissance eras of both Middle Eastern, and European civilization, people started to do what was known as alchemy. Alchemy is the foundation of chemistry. One of the premier experiments that people tried to do is they would try and turn abundant elements like lead into more rare elements like gold. Turns out that you can do that, but there was no way they were going to do that in 1580 because you need a super collider, and you need to basically split a lead nucleus into get rid of 3 protons somehow. That's very difficult and expensive to do. It's cheaper to just mine up the gold. But all of the experiments that they did during that time helped them figure out, like, oh, this reacts with this other thing, and then I make this new thing, and that new thing is useful to us in some way. And going on to today, this is actually from the laboratory that was across from where I worked. I worked in the Goldberg lab, but the Kovacs lab did a lot of physical chemistry and inorganic chemistry with lasers and cameras and stuff like that. Going on to build upon the knowledge of alchemy from the 15th and 16th centuries, and all of the stuff before that, we've started to gain a really good understanding of how stuff works at the atomic level. So, to summarize what is important for this class, the foundational message that we want to say is that chemistry is how does matter transform? When I put matter A into contact with matter B, does it react or does it not? And we want to know the answer to that either way. For example, things like your clothing should not react. If you put on your clothes and then they started to, like, burn your skin, that's a problem. Perhaps we shouldn't make clothing out of sodium, for example. Likewise, if you're trying to make something that is supposed to generate heat for, like, a heat pack or something, you don't want to use water because it's not going to do anything. So doing all these experiments is really important, and for the most part, we've done a lot of experiments. The point of this class is to look at some of those experiments, but more or less look at all of the information that people have covered up until this point and give you the brief summary. Brief being kind of a tongue-in-cheek term here. Now, this chart shows you how chemistry is linked to other things. Of particular importance to you probably are going to be things like physics and mathematics, material science and engineering, and biology, depending on what major you're doing. But all of these things lead back to chemistry. So we're going to use chemistry in a foundational way, and we're going to use a basic understanding of math and physics to help us explain what's going on here. If you've never taken any sort of physics class, you're going to have a sort of crash course, introductory physics, going through this quarter. Hopefully you have some sort of math background, because the prerequisite to get in this class is being eligible for pre-calculus. We aren't going to do any calculus in chemistry. We're going to only do algebra. That's going to involve things like unit cancellation, logs and exponents and stuff like that. And as those things come up, we'll briefly review how to do them. Once you're done, you'll be able to apply this chemistry knowledge to things like biology and engineering. Now, everything around you is involved in some sort of application of chemistry. Believe it or not, chemistry is extremely ubiquitous, probably even more so than physics. For example, every day you have to eat something. Food contains energy. You don't just eat stuff because your body likes food. It wants the energy that's in the food to drive chemical reactions that are physiologically important. For example, moving ions around your cells so that we can generate ATP, so that your mitochondria have energy so that you can do things like move. Moving is obviously very important. We're going to cover that in Chapter 9, which is Chem 162. If you have your phone handy, on your phone, if you turn it on, the screen will broadcast information to you using light. Light is going to be something we do cover in this class. That'll be Chapter 3. How is light generated? Well, there must be something inside your phone that is creating that light. It is actually an LED of some sort, and the materials in the LEDs are basic elements that we're going to cover. How does the battery work? We'll talk about that 163. My slide says the seat that you're sitting on is made of plastic, but that's only true if we were in the classroom. You may be sitting on a different sort of seat. I'm sitting on a leather chair right now. But leather is an organic substance that is generated by animals. Organic chemistry will cover a lot of those things in 261, 263 if you have to take it. But the point of this whole series is to just go over, like I said, how all of this matter behaves and how we can manipulate it. We're going to do a lot of manipulating matter, and that's kind of the whole point. What manipulations are possible? All right. In order to study any sort of science at all, not just chemistry, but anything, we need to have a sort of a blueprint. We can't just really blindly go in and say, I'm going to do an experiment, and then I'll just sort of randomly put things together and hope for the best. That's how science started out in ancient times, and since then we have developed what's known as a philosophy. A philosophy is a set of rules that we have to follow in order to call it science. If you've ever watched Mythbusters, one of the things that, I want to say it's, I don't remember his name. The guy with the goatee. He says frequently that the difference between science and messing around is writing stuff down. And that's very, very true. The most important thing that we're going to do in this class is take information and record it. Once we've recorded it, we can then assess that information. And so the way that we do that is we follow this sort of blueprint right here. So you should be able to see my cursor. I think I'm capturing the cursor. I can see it on the preview window. At the start of any sort of curiosity or interest, you're going to make a mental note of something that happens. For example, if you grabbed something on your desk and you lifted it up and you let it fall, and you should be able to hear that it fell, you could make an observation that, hey, if I drop something, it seems to go in the downward direction. So those would be observations that you could make. From that information, you could then make what's known as a hypothesis. Let me put that on the board here. A hypothesis is some sort of prediction or guess about future phenomenon based on information that you have. For instance, if I dropped my phone and it falls to the ground, I could make the hypothesis that anything else I drop would also fall to the ground. Now, if I drop my glass of water, it would be a lot more messy than dropping my phone. But in order to know that it would fall to the ground and spill everything everywhere, I have to actually do the experiment. If you don't do the experiment, it's just a hypothesis. You might want to make a hypothesis that's a little bit more specific. So you might say, I think all things will fall to the ground at the same speed, or they will all bounce, or they will all just go thunk and not bounce at all, or things like that. What you need to do at that point is then actually do the experiment and make more observations and collect more data. If you were dropping something heavy and dense, like your phone, and then you dropped something that was not very dense and had a big surface area, for example, like a sheet of paper, you'd notice that the sheet of paper would fall very slowly relative to the phone. That data will help you learn something about how objects fall. Hey, maybe their surface area is important. Maybe their mass and their surface area is important. If you do enough experiments, you start to develop a clear picture, and that's what this is right here. Getting information will contribute to a body of knowledge that will help you understand how the world around us works. This sort of loop here goes in a circle. We're going to keep doing experiments and making new hypotheses until we refine an understanding that creates a sort of rule. And those rules are going to be this information over here, where we have an observation that becomes a law or a theory. The first terminology that we want to talk about are facts. Scientific facts are the results of experiments that support hypotheses. If I say that all objects fall down, and then I find something that doesn't fall down, that's not a fact. But if I do an experiment where everything I do matches with my hypothesis, we can accept it as fact. Some examples of scientific facts would be, hey, if I put sodium in water, it always explodes. Sodium the metal, not sodium the salt, for example. If I pour water on the floor, it always evaporates if the temperature is at a certain temperature and the amount of water in the air is at a certain condition. Some hypotheses are more rigorous than others. For example, water won't evaporate if it is very humid in the air. We might have to include those things. Once you have created enough tests to get a general picture of what's going on with all sorts of matter, we can move on to what's called a law. A scientific law describes how matter behaves, and we can use observations over different experiments to determine if matter always behaves in the same way. For example, if I have iron metal, iron will rust if you get it wet and you leave it out. But will chromium do that? Will tungsten do that? Will nickel do that? Some metals will rust and some metals don't. So iron metal rusting would be a scientific fact because it's very specific and we know it's true. But could we say that all metals rust? And it turns out the answer is no. So we could not use that as a scientific law. We could, however, say a scientific law would be that all metals will corrode when exposed to something like, say, chlorine. Again, we have to do those experiments. The last bit of information that we can do is we can devise what's called a theory. Now, scientific theory is actually really, really, really detailed and nitty-gritty in terms of what it explains. Scientific theories describe why matter behaves how it does. For our metal example with reacting, say, with chlorine, what you would say for a law is that, oh, all metals will react with chlorine and corrode and then become brittle. But for the theory, what we would then say is chlorine will react with metals because chlorine will take electrons from the metals and the metals are willing to give them up. In doing that, they form an ionic compound which has different properties from the original components. Now, if all of that kind of goes over your head, that's okay, because we're going to talk about those things as the quarter goes on. But as you could see with the theory is a lot more detailed. It tells you what exactly is going on at the atomic level, why we care specifically about these elements, what process is occurring between them, and not just sort of putting a blanket over it and saying, this is what happens. The law is just the vague generalization. The theory is very specific. So the take-home message here is if you hear someone say it's just a theory, that person's an idiot, and they don't understand basic science. Theories are really important. All right. So this page will demonstrate what several of these do. I don't have a window capture to show these videos, so I'm going to click on something, but I need to actually mute this audio really quickly. I don't know what will happen when I do this. Okay, so what I need to do is I'm going to go to this window. I'm going to capture a window. So this is my technical difficulties part. So YouTube video. Okay, so I got the right thing in here, but I don't want all of this stuff. So hold on just a second. I misclicked, so I don't need the top. I don't need any of this stuff down here. And I don't need any of this over here. Alright, so this video shows, and I apologize that's not really centered super well. This video is going to show what happens when we put sodium into a trash can. And the trash can is full of water. So here we go. We'll turn up the volume a little bit here. Okay, so you would see that, well, that was interesting. Okay, if we drop water and sodium into the same area, it kind of goes boom. Okay, but does it always do that? Like, this guy seemed to put it in a package. I mean, this can of water is not very scientific, obviously. So we're going to use that as our... Let me go back to this screen. That's going to be our first experiment with sodium added to water. I'm going to do the second experiment. We're going to click on this, and presumably it should open in the same page. So now if I do this, okay, there it is. This is video 2. You can see that this is a much more official and scientific showing of what's going on here. This person has sodium on the end of some sort of tool. Okay, so what happened there? It seemed to go off like a gunshot. You could see that there were some similarities to this experiment and the previous one that was done. Let's now go to number 3. This one is going to be a microscopic version of the experiment, where a small amount of sodium at the end of this forceps is going to be put into water. I realized that I didn't unmute the video or the audio, so now you should be able to hear stuff. I apologize for that. So we'll show that experiment again. Okay, so thanks for calling that out. So if there are technical difficulties, let me know, because I have buttons that I can hit here, and I may accidentally push them when I don't intend to. All right, so let me mute this screen. Let me go back to here. So through all of those experiments, you probably noticed the same thing happened over and over and over. Sodium, when added to water, it went pop. It went boom. It was very quiet in the first 2 examples, but that was not a feature of the sodium. That was a feature of me. What scientific fact do you observe from that? Well, you would say, okay, sodium must be reactive with water. It explodes. Now, can we extend this information to other phenomenon? For example, I want to make a law out of this, but a law would require more than just sodium. A law would require me to say, okay, maybe all metals do this. Well, if you put iron in water, it doesn't explode. Otherwise, every time you go out driving when it's raining, it would be a very precarious situation indeed. But some metals do explode. If you have access to a periodic table, and you should, because directions for that were in the syllabus, you could quickly go to this address. I'll type it in the chat, so www.ptable.com. That didn't actually link. That's okay, though. ptable.com. I just want to make sure I type that in correctly. And what you'll notice is that, and this should capture this, that's good enough for my purpose. You should notice that the metals that we're going to be using are going to be all along this side here. We looked at sodium. For the next few experiments, we're going to look at potassium, rubidium, and cesium and see if something similar happens to them. So let's give that a shot. So here's potassium. And this is going to be the same sort of setup as before, where we drop something into the beaker water. And what I want you to do is, when you watch this, I want you to consider, is this going to be exactly the same as the sodium one, or is it going to be similar? So here's the potassium. For comparison, here was sodium again. So you could see that there were very clearly some similarities and some differences. If you were asked to describe these differences, you could say things like, say, oh, it was pink instead of orange for the potassium. That's interesting. Or the potassium example was way faster, or it popped bigger. But at its core, the behavior was pretty similar. So we could say that, hey, potassium also will burn in water, and it will explode very quickly. Yeah, so they were both exothermic. Exothermic being energy was released. For the next one, I think that this video isn't actually what I want. Let me see if this links to the correct thing. No, it doesn't. So let me close this. Search. I want rubidium in water. Okay, there we go. So now I've got it up. So this is rubidium in water. This is the next element down on the periodic table. So here we were at potassium. We're going to go down to rubidium. Now, based on our trend here, going from sodium to potassium to rubidium, could you make a prediction about what is going to happen? And you can type it in the chat if you want, or you can keep it yourself. But try and make some sort of guess what you think is going to happen when I hit play here. And yes, my cats are bothering me right now. I'm trying to scare them away. All right, so let's see what happens. Here's rubidium and water. Was that everything you hoped for and more? So what I'm going to do now is play it again, but it will be slower this time. And now it sounds like a video game. So there you go. So was that faster or slower? It was a lot faster. Now we can do cesium. Let me go back to his page here. Cesium in water. All right. I had to pause this one really quickly. This is cesium. Blink and you'll miss it. I think I unpaused it and I lost a frame there. Let me try that again. There you go. That was cesium. Here it is in slow motion, 1 frame at a time. And it doesn't last at all. So you are noticing some differences, and that's good. So you're thinking like a scientist. These aren't exactly the same things, but they do behave similarly. And so because of that, we're allowed to make the conclusion that metals in this grouping... Oops, let me go back to my periodic table there. Periodic table. Metals in this grouping tend to behave similarly. I unfortunately can't do francium because francium is radioactive, and it's not online. What we could do is we could pick a different element that's not in that group. So let's do that. Let me do this while I search for it. Just in case anything bizarre shows up, which has happened before. Alright, there we go. So we'll unmute. So this is what calcium looks like. This is calcium metal. It's very different than the calcium in your bones. So when we get to the lithium part, I'm actually going to ask you to predict that, and then I'm going to show you the answer. But here's calcium. Calcium is in a different spot on the periodic table. Let's see how it behaves. What do you think? What's the verdict on that? Same, similar, totally different. Yeah, calcium just sort of hangs out. It's like, I'm going to slowly and casually react. So we would conclude from this that the elements that we tested, being that they're all in the same row, maybe that has something to do with it. Maybe elements in the same column, sorry, not row, column, columns are up and down, are all reactive with water and will burn and pop and catch on fire. Whereas elements in different columns might do something differently. All right, and I haven't forgotten about lithium, so don't worry. All right, so our message here is that for scientific facts, we can make facts about each of those things that we saw. So we could say that, oh, well, sodium explodes and it burns orange, and potassium explodes and it burns pink. But a scientific law would be more general to a bunch of experiments. So we could say elements in the first column of the periodic table all explode when combined with water. Now, could we make a theory out of this? Well, just by watching these YouTube videos, no, because we don't know why this happens. If we put water into these metals, They burn, but something must be happening between the water and the metal. What specifically is that? We're going to talk about that in Chapter 3 of this course. So let's go back and answer a few of these questions here. So allergic to water is that's a good enough sort of analogy. Yeah, they interact with water and they react violently. They do dissolve over time. Dissolving is a little bit of a different word than I would use. We're going to use the word dissolve to describe something like table salt dissolving into water. These things that we're putting in there do eventually dissolve, but they react first. So reacting and dissolving are different terms, and we'll use them in different contexts. Let's go back to the lithium real quick. So a bunch of you had some ideas about what lithium would do. So you've seen every other element in this column. If I drop lithium in there, what should happen? So we got to do this. So I got to go back to the previous page because he has lithium on there. Oops, that's cesium. Hold on. Lithium in water. There we go. So here's lithium. And is it everything you hoped for? I hope so. So if you assumed that it would burn slower because it was higher up on the periodic table, then congratulations, you're thinking like a scientist. Things seem to get more reactive as they go down the periodic table. I don't have the answer for why that happens for you right now, but when we do Chapter 3 and talk about ionization energy and electron configurations, it will become much more clear, and we'll talk about that in more detail at that time. All right, let me clear out some of these windows because we don't actually need them all. I don't want my computer to explode. All right, so that's scientific facts, laws, and theories. For our next little discussion, what we're going to do is we're going to investigate some properties of... So I've already talked about this, so this is what a theory is. Theories are very difficult. We're going to talk about theories later on as we go through this course. Let's see here. So we can't say that the atom is splitting apart because we don't have information that shows that. All I showed you in the video was that things catch on fire, but at the atomic level right now, we don't really know what's going on. We're going to investigate that in more detail using experiments in Chapter 3. What I can tell you is that the electrons are what are involved in chemistry. Generally, the atom itself, the nucleus, isn't going to be doing much. But there is some interesting stuff that we can talk about in later chapters when we talk about nuclear chemistry and so on. On the screen here, you'll have my description of the atomic theory of what's actually happening to our matter. None of these words should make sense to you. Periodic table, explosive, single S electron, ionized, exothermic reaction. That's okay. We're going to get there. So theories will require a lot of nitty-gritty details and a lot of knowledge that we just don't have yet. So we'll get there. And again, if you hear someone say it's just a theory, that person doesn't know what they're talking about. I'm talking about specifically a person on YouTube that does a channel and talks about game theories. As a scientist, that makes me sad. Anyway, moving on. All right. So on the board here, I have a sample experiment. I have 2 experiments, actually. And what I want you to do, very briefly, for about 2 or 3 minutes, is go over these questions, writing down what you think each statement is in experiment A and experiment B. I want you to classify it as either a fact, a law, or a theory. Shots fired. Don't worry, that person will never find this channel, I hope. All right, so I'll give you a few seconds to do that. I'm going to go get my water, and I'll be back in just a moment. Oh, sweet. I can draw all over this, too. All right, so we're going to go over the answers because it looks like a bunch of people are coming with ideas. Let's talk about experiment A. One of these is a law, one of these is a fact, one of these is a theory. So from our definitions of these terms, a fact describes a very specific experiment. A law would describe a group of experiments. And a theory would describe what is happening at a very, very high level of detail. So going through that, I can't use the mouse to do this. I gotta use my pen. So what I would do to solve this problem is first I would say, okay, so let's look for the fact. The fact should be the most general thing for one specific experiment. So if I looked at these three statements, which of these could I immediately cross off the bat as being a fact? Heat moves through molecular vibrations. That seems really specific, so I'm not going to call that one a fact. The final temperature of two objects in thermal contact with one another is their average temperature. That seems like it would be a broad variety of experiments, and not one specific experiment. But this first statement here, mixing boiling water and cold water makes a solution that is lukewarm. One, that's true, and B, that's a very specific experiment. So we could say that this is a fact. And that appeared on the screen. Hooray, that's actually working. Now let's find the law. Let me get a different color here. I don't know if I have a different color. Oh, I can. I have all the colors. Look at me. Let's do green. So now let's do a law. And the law is like the fact, but it's for a more broad assortment of experiments. And so between the two of them, I lost my cursor. Where's my cursor? There it is. This one is the best described as the law because it describes generally what is happening for a broad range of experiments. Finally, we have the theory, and by process of elimination, that must be this. And the way that we can determine that this is a theory is because this is telling us something that is happening at a very specific level of detail. Heat moves through molecular vibrations. When molecules bonk into each other, they exchange energy, kind of like how anything bonks into something and exchanges energy. When you do that with small enough particles, we interpret that, our bodies interpret that as heat. All right, so the answers for the first one are the first statement is a fact, the second statement is the law, and the third statement is a theory. That was pretty straightforward. I didn't even scramble them. I did that a little bit more on the second one. So for experiment B here, trying to find the fact would be for a very specific experiment. Which of these is the most specific for our experiment? So here we have sodium chloride mixed with water. That seems pretty specific. But then it goes and tells us a reason why. And that reason why would make that a theory. So let's mark that one first. If I could click on the thing. Where's my blue? There it is. So this one is the theory. Oh, I clicked on my pen somewhere. I have buttons on the pen, and I don't know what they do, and now I do. So I gotta stop putting my fingers there. And the reason that this is a theory is because this information here tells us... Ooh, look how straight my lines are, you guys. I'm really good at this. That information tells us what is going on at the molecular level. Having a high concentration of solution forces water molecules out of your cells. This is why you get dehydrated if you don't drink enough water. The amount of ions in your blood are too high for your cells to maintain their integrity, and water moves out to create the same concentration. This is called osmosis. We talk about osmosis in 163, I think. Let's find which of these is the fact. So of the two, which is the more specific experiment? Just a flower or any fruits and vegetables? Well, of those two, the flower is going to be our fact. Hey, if you put a flower in salt water, it's not going to grow. In fact, it kind of dies. Don't drink salt water, it's just bad. That must mean that this last one is the law. Vegetables and fruits do not grow well in areas with high concentrations of ions in the soil. Alright, I hope that those two experiments helped illustrate the difference between a fact, a law, and a theory. On an exam, I'm going to give you something very similar to a group of statements like this, and your job will be to identify which is which. The last little bit we'll do for this first section is talk about domains. We've been talking a lot about the microscopic level and then everything else. The term for the everything else domain is the macroscopic domain, and this is basically what you see. So if you go look outside, everything you are seeing is the macroscopic domain. In fact, you don't even have to go outside. I just want you to go outside because it would be nice, right? If you were to zoom in on the macroscopic domain really closely, and I mean really closely, like electron tunneling microscope level, what you would actually see is called the microscopic domain. The microscopic domain is just too small for us to see normally. We need to use our imagination to understand what's going on here by interpreting things at this level. Hold on, let me get my arrow back so that we can see the arrow. So these pictures are imagined pictures, basically. This is an artist's conception of what atoms and molecules look like. They don't exactly look like this. They're certainly not like these giant red spheres floating around with two white spheres attached to them for water. But for our purposes of understanding, we're going to interpret molecules at the microscopic level as sort of like this. We're going to do some work with drawing structures of molecules in this course. We're going to draw Lewis structures later on. But for now, we're going to start with just very simple concepts of like, oh, at the molecular level, it's just a bunch of balls and spheres bouncing around, and that's fine. But whenever I say something is in the microscopic domain, this is what I mean. When I say something is the macroscopic domain, I mean everything else that you can see. We're going to be primarily using the microscopic domain to explain theories and things, but the macroscopic domain will be important to describe laws and facts. The last domain that we care about is the symbolic domain. Drawing pictures is hard, you guys. I don't know if you know this, but even though we would be in the art building, people dedicate their lives to drawing these pictures and creating these things. I'm going to stick with this notation that I've boxed in green, and that's called the symbolic domain. I'm not going to actually call it the symbolic domain by name, but we're going to pretty much stick with me just writing the word H2O to represent this little guy right here. And as we do more work in chemistry, you'll start to be able to envision these molecules by just their formulas alone. All right, that's the first section. Now that we have an understanding of how science works, we're going to try and categorize matter into different sorts of arrangements based on what it can do, how it interacts with itself, and some different connotations of like how heat behaves with it and so on and so forth. So first let's talk about phases. What are phases? Oh, I guess first let's talk about matter. These are all things that exist in the world. One of these is actually on my desk right now. If you guessed the balloon wrong, that's not on my desk. If you guessed coffee, no, I don't drink coffee. It must be this guy. We define matter as anything that has two specific properties. Those properties are the following. And I gotta get my pen again. There we go. The most important things that are for this are that matter occupies a space. Only one thing can occupy space at a time. And the other property of matter is that it has mass. Mass means that it is made of matter. So that might seem like a little bit of circular reasoning. Yeah, I don't drink coffee. I don't like hot beverages. I just sleep like 30 hours a day. That's how I stay awake. Anything that has these two properties, we're going to call matter. We're going to define matter into different sorts of forms that we encounter all the time. And those forms are going to be solids, liquids, and gases. And each of them has their own unique properties. There is a fourth phase of matter that is pretty common. The plasma is things like fire, the sun, electricity. Those are things that we're going to realize that exist. We're not going to actually study plasmas very much, but they are out there. There are other phases besides these three main ones. We're just going to stick to the three primary ones and try and define them based on properties that we observe. On this table here, I have some properties categorized by shape and volume, and you'll notice that for each of the three common phases of matter, solid, liquid, and gas, we can actually distinctly categorize them. For example, a solid has a rigid fixed shape, and its volume by definition must not be able to change if its shape is fixed. Liquids have a variable shape. They will take on the shape of their container as shown up here. However, the volume that they will have will be the same. If you have a really tall cylinder, let me get the pen back out here. So if I had something that measured something like this, and this is the 10 mil mark, and then I had another container that was really wide, and this was the 10 mil mark, and I were to put this content into here, both of the containers would fill to the fill lines. Even though their shapes are totally different, their volumes would be identical, because that's how liquids behave. I don't know, maybe that brown liquid is, like, Monster. I don't know. Finally, for gases, gases fill the entire container. Gases have a variable shape and volume. If I were to change the shape of this volume by maybe, like, pushing this cork down so that it blocked off this much, then the gas would then occupy only this space. I would still have the same amount of matter in there, but its volume would change and so would its shape, because I've changed the volume that it's allowed to be in. So those are the basic phases of matter. You'll be asked to distinctly identify all three of them based on their properties. Now, what can we do with this stuff? Well, we can talk about different properties that matter exhibits. So, for example, the space that it occupies is its volume. Volume is very important for us to understand because volume is a property that we can measure very easily. Mass is the stuff that it is actually in there. For a gas, like if you take a deep breath, and then you let out all that air, about 99% of what you just breathed in is empty space. It's just a void. There's actually not that much matter in the air around you. Whereas if you grab your phone, or you grab a mug that has water or coffee or beer or meat or whatever it is you're talking about, the matter in those phases is going to be packed much more densely. Both of these things can be measured, and we're going to use those properties later on when we start doing numerical analysis with these. I know, I yawn, and I heard 70 other people yawn. Haha, I'm in complete control. We're going to use these two properties, volume and mass, to describe other properties from that. The first one we're going to talk about is weight. Weight is how much matter you have that is affected by gravitational pull of wherever you are. Weight and mass are very different from each other because gravity is involved with weight, but it is not involved in mass. For example, if you weigh 100 kilograms on Earth, you will also weigh 100 kilograms on the moon. However, your weight, which we would measure in pounds because we live in America, if you live in, like, Britain, you would measure it in stone. If you live somewhere, like in a laboratory, the way that weight is actually measured is in newtons because weight is a force. So your weight on Earth is going to be different than your weight on the moon because the force of you pushing against the surface of whatever planet you're on will be different due to the lessened gravitational attraction of the moon. So everybody occupies a space, everybody has a mass, but everybody will have a different weight depending on what planet you're on. So the universal traits here are mass and volume. Weight is not universal. And everyone matters. That's correct. Very good. See, science is easy. All right. When we do reactions, I'm going to just put everything on the board here. Since you guys were talking about beer, here you go. Have some beer. When you do a reaction, the chemical reaction that occurs involves the matter that is present. But what is happening between the atoms and molecules that are involved is they're just rearranging. They aren't actually disappearing or being destroyed or turned into nothing, like they're not annihilated. This principle is called the law of conservation of mass. And the example that I have here is that if you make beer, like for example, if you brew beer, you put a bunch of stuff in there, and you put it in a bottle, and then you leave it to age. And when it ages, what happens is that the bacteria that are in the beer, like the yeast basically, will consume the sugar, and they will ferment it, which produces flavors and carbonation and other stuff. And then after enough time has passed, we then get the result of that, which is presumably good beer. And then you consume it, and then we're happy. Now, that's the subjective, opinion side of things. Let's talk about the science part of this. If I were to weigh this sealed bottle before and after I did this experiment. So, for example, I gotta find my cursor again. There it is. So let's suppose that this weighed, 835 grams. And you'll notice that I used the word weighed there. Colloquially speaking, in this class, when I weigh something, I'm going to determine its mass. I don't really care about its weight in terms of, its force that it exerts, because we're all going to do all of our experiments on Earth, and gravity is roughly constant no matter where we are. So just be mindful of the differentiation between weight and the verb weighing. So let's suppose that my beer weighed this much, had a mass of 835 grams. After the experiment, if I weighed it, I would find that it has exactly the same mass. And the reason for that is because matter cannot be created or destroyed in a chemical reaction. Everything that was in this container is still in the container, and therefore it will have the same mass. Now, if I were to open the container, then what would happen is that anything that was in the gas state would evaporate away, or it would undissolve out of the solution and then escape. I obviously can't weigh that if it's not in the container anymore, and therefore the mass would change. So there is a bit of an illusion that the law of conservation of mass might not be valid for some things. For gases in particular, this is what you have to watch out for. If you have a reaction that produces a gas and it's not a closed container, you'll get a different mass. But for all experiments that we do in this class, we're going to make the assumption that the law of conservation of mass is true, because every experiment that has been done has more or less verified this to a very high degree of precision. And so we're going to consider it as law and work with it from there. I don't actually know if that's a big beer. I guess that would be pretty big. That's almost like 2 pounds of beer. I mean, I don't judge, so. Alright. Here's another example. On the board, I have a chemical reaction here. This is Alka-Seltzer. In Alka-Seltzer, you have sodium bicarbonate and citric acid. And when they react in the water, they bonk into each other. In the compressed tablet form, they can't actually find each other because they're solids. Solids don't move very much. But when you put it in the water, the substances dissolve, they move around, they encounter each other, and then they react. One of the substances that is made during the reaction is this. This is the fizzy thing that you see in a reaction, CO2. When you do this reaction, you get a carbonated beverage that helps relieve stomach indigestion. You can then drink it. It tastes absolutely awful. Don't drink Alka-Seltzer by itself. Sorry, I read your question and I lost my train of thought there. So going back, why is it a law and not a theory? So at the atomic level or the molecular level, we don't really have an explanation for why the law of conservation of mass works other than just everything stays there. You aren't really losing any protons, neutrons, or electrons. Also, the reason that we can't really say it's a theory is because for all processes, the law of conservation of mass isn't actually true. It turns out that when we do nuclear chemistry, we do lose matter. But that's actually beyond the scope of Chem 161. So there are extra situations that aren't contained in chemistry that go beyond the law of conservation of mass and actually say, oh, this doesn't happen. In fact, we do lose mass. We turn it into energy. In fact, you've probably heard of the equation E equals mc squared, where energy is E and mass is m. They're actually related. Yep, so matter can be converted into energy, but it requires a very intense reaction to do that, and no chemical reaction can do that. That's actually a nuclear reaction. We'll very briefly talk about nuclear reactions, but for chemical reactions, the law of conservation of mass is essentially a theory, but because it doesn't encompass everything, we have to call it a law. On the board here, I have 10 grams of Alka-Seltzer and 50 grams of water. I think 10 grams of Alka-Seltzer is actually a lot of Alka-Seltzer, too. I'm not good at estimating masses, I guess. If I did this experiment, and then I weighed the cup with the water in it, and I teared out the mass of the cup, and I found that the solution's mass was this number right here, 57.9 grams, you could conclude that some of the matter had to have escaped. And I've already told you that the CO2 down here... Oops, I gotta get my mouse back. The CO2 down here is the gaseous component that left. So if you were asked, hey, what was the mass of CO2 that you made in this experiment? You would simply just take the difference of what the components are. And that would just be... I gotta find a space to write here. We'll do this. If I just subtract these two things, and I really hope that I did my math right. I know, we all want to do nuclear chem right now, right? No, we gotta do the normal stuff, because I can't make the assumption that everybody's taken 140. So we would conclude that 2.1 grams of CO2 is how much stuff was there, because we're going to assume the conservation of mass is valid. I'm just checking my clock here. All right, so it is 2 p.m. Every hour we take a break. Yep, so we're thinking the same thing, so that's good. So what I'm going to do is I'm going to put up... I didn't actually make a break slide. And I don't... Oops, that's not what I want. Let me do... I'm going to put the title card back up. I'm going to add some text here. So add text. Break. Time. Let's see here. Oh, I gotta do this so that I can select what color it is. So break time back in 10 minutes. I want it to be white. And we'll put this on the board here. We'll make it really big. And then I should probably put a timer on the screen. Let me get my timer out. Split. So go ahead and take a break if you'd like. I will put the timer on the board here. So window capture. Timer. That's not what I want. That's what I want. All right, let me start the timer. And we'll be back in 10 minutes. I will turn the music back on just so I'm not playing dead air. And I'll see you in a bit. Yeah, I do use Live Split. Now I gotta see if I can stop the timer exactly on 10 here. Oh, I hit the wrong button. That's okay. Let's see here. Let's need this. All right, we're back. Let me go back to the lecture slide. Let me see some questions that we came up with. So getting a few questions that are off topic. Let's try and keep stuff on topic here. Where is the homework problems? The homework problems are in the, if you check the online textbook, they are in the section that says exercises. During this class, can we assume the law of conservation of mass is always true? Yes. We are going to exclusively work within the confines of the conservation of mass, because we're not going to be doing any nuclear chemistry. So we don't have to worry about atoms splitting into smaller atoms. In fact, on the next slide, we're going to talk about atoms in just a second, like what they are. And we're going to assume that they are these indestructible little spheres that we can't divide and lose matter from. In fact, that's where we're going right now. So let's talk about the atomic nature of matter. For our thought experiment, what I'm going to give you is a sheet of copper. And I don't know why it's blue. Probably because if I made it the actual color of copper, it would be hard to see the word copper. And what we're going to do for this thought experiment is we're going to take our copper sheet, and I'm going to cut it in half, and I'm going to do this to it. And then I'm going to cut it in half again, and again, and again, and again, and again, and again, and again. And I'm just going to keep doing this over and over and over and over and over again until I get to the point where what I have left can't be split into a smaller piece. That tiny, 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 tiny piece that we have is what we would call an atom. If I cut that in half, I don't have copper anymore. So the smallest fundamental piece that we can have and still call it copper is what we're going to describe as an atom. Now, atoms are made of other things. We're going to discuss that in a little bit more detail later on. But for now, we'll just treat atoms as these spheres. If I have a copper, it's going to be a sphere that has these specific properties to it. What those properties are, like the number of protons and electrons and neutrons it has, we'll define later. How do we represent atoms in structures? Well, here's what they look like in reality. On the left here, I have a lump of gold. On the right here, this is a scanning tunneling microscope. Each of these little dots that you see is actually a gold atom. Now, for our representation, thinking of them as spheres is good enough, really, because if you look at them to the highest resolution that we have available, they essentially look like spheres, and you can see them here. How big are atoms? These are the numbers that are quoted in terms of mass and how many you need to have the mass of 1 gram. So a single atom of gold is 3 times 10 to the minus 22 grams. That is incredibly small, like unfathomably. I cannot even conceive something that tiny. By the same notion, this number here, 3 times 10 to the 21, is so ginormous that if I gave you like 10 to the $21, you wouldn't know what to do with that, because that's more money than exists on the planet by orders and orders and orders of magnitude. So the numbers that we're going to be working with are going to be extremely tiny and extremely big. So wrapping our heads around this sort of numerology is going to be a real challenge in this course. Like, how do you conceptualize times 10 to the 20 of something? We're going to try and make a few analogies as best we can when we get to describing molar mass and atomic weight and things like that. Now, do all atoms exist independently? The answer is no. Most matter exists in the molecular form. Molecules are collections of atoms that exhibit forces that hold them together, and these are called bonds. For example, if I were to draw water with my pen here, this is what we were drawing before here, and this blank atom is oxygen. There's really no way that I can write an O inside a circle and have it look like anything other than just 2 circles, but this is what we represented our molecule as before, on those little diagrams, where the O was the red sphere and the hydrogen were the two white spheres. This is called a molecule, and in my description here, this line that I drew right there is what's called a bond. Bonds are essentially tethers. They hold the two atoms together, and they don't fall apart under most circumstances. A lot of chemistry is exploring the nature of how molecules interact and how these bonds are formed and reformed and destroyed and how we rearrange atoms to get stuff. These atoms up here on the top, let me get the highlighter up here. So these guys right here, these just exist as independent atoms that float around on their own. So for example, if I have xenon, here's xenon floating around on its own. It doesn't have any bonds to anything else, and so it'd be independent. We're going to call things like that. Oh, goodness, everything's terrible. Hold on. I hit the back button again. We're going to call anything that exists independently an atom. This whole collection is going to be called a molecule. But each of these independently are also called atoms. Okay? So the difference between atom and molecule is a molecule is just a bunch of atoms stuck together. I'm going to hit the spacebar, and then immediately text is going to appear over my drawing. That's okay. You can still see more or less the rest of the diagram. On the bottom here, I have a bunch of formulas. So again, here's the symbolic notation of these formulas, so on and so forth. Note that when I have this little subscript here, that is showing that I have two things linked together. If I have a complex molecule with a bunch of things that are all joined together, I will just write them all as one formula, and these are all connected together in a very specific way. This is connected to this, which is connected to those. And I'm just going to start drawing lines here. Are the five gases atomic because they're noble gases? Yes. So specifically the noble gases exist at the atomic level as individual atoms. There are some exceptions to that, which we might talk about in chapter 4. Yeah, 4. Xenon does some really funky stuff if you put fluorine or oxygen with it. All right. So now that we've talked about molecules and stuff, and we know how matter occurs at the microscopic level, let's try and expand that to the macroscopic level and talk about, well, one of my favorite things, cake. On the screen here, I have some water and I have some cake. If I was going to ask you to describe one of these as pure, which of them would you categorize as pure? Now, unfortunately, the answer is not pure cake. If somebody does know where to get pure cake, please tell me. I would be very much appreciative. No, the pure substance on the left, water, is pure because there is only one thing in there. It's water, right? So, if we have a container that holds only one substance, that substance is going to be considered a pure substance. And so you can do this with anything that you can really ascribe to one type of atom or molecule as. So you can have pure sodium, you could have pure salt, you could have pure water, but you can't have pure cake, and you can't have pure soda, and you can't have pure cheeseburgers. I'm just listing all the things that I want because I can't go out and eat them. We're going to categorize those foods and various other things that have a whole bunch of different chemicals in them. We're going to call those mixtures. Now, for instance, if you grab something off of your shelf in your pantry or your fridge or whatever, and you look on the side of it and it has a list of ingredients, then by definition it must be a mixture. If the ingredients list only says one thing, then it's a pure substance. For example, if you grab your soda and it just says water, then congratulations, it's not actually soda. You've been hoodwinked. But a bottle of water that literally only has water in it would be a pure substance. A box that contains table salt, for example, would also be a pure substance, because the only thing that's in there is salt. If you have salt that also contains iodine, for example, some salt is supplemented with iodine to promote thyroid health, that would not be a pure substance. That would be a mixture. That would be mostly salt with a little bit of iodine in it. In order to categorize our matter, we're going to make this little flowchart here. And we're going to ask ourselves a bunch of questions at each junction to help us define what the matter is that we're interacting with. And our first question, does it only contain one substance, helps us to differentiate between pure substances and mixture. What we're going to do now is we're going to look at pure substances, and we're going to try and split that category into two other categories based on what we see inside. On this screen, I have two things. One of them contains only one type of element, and the other contains more than one type of element. Now, if you know enough about table salt, and maybe not necessarily anything about diamond, that is a diamond on there, by the way. If you know the formal name for table salt, you would recall it as, sodium chloride. Well, sodium and chlorine are two different atoms on the periodic table. Where is my periodic table here? So I gotta do... Oops, that's not what I want. I gotta just make this a little bigger. If we look on the periodic table, sodium is right here, and chlorine is on the other side right here. Those are two distinct elements that we have inside this container as sodium chloride. So this substance down here, the table salt, contains at least two things. Diamond, on the other hand, only contains one thing. Turns out that one thing is carbon. If you have a substance that contains only one type of atom, and it's completely that atom, we're going to just call it an element. Diamond, for instance, is just carbon atoms that are all bonded together. And if you cut it in a certain way, it looks really pretty. But at all of the edges and in all the inside, it's just carbon atoms completely. If you tried to break it down into simpler substances, you wouldn't be able to do that, because all you would end up with is just more carbon in different pieces. Elements only have one type of atom. The table salt, on the other hand, has two atoms in it, the chlorine that we identified before and the sodium. Both of those atoms together combine to make the table salt, so we would say that table salt is not an element. It contains two elements. Because there are two elements in there, there's two types of atoms, we're going to call it a compound. Compounds have multiple elements in there. Two is not the requirement. You could have more than two. You could have 3, 5, 8, whatever. But what compounds can do is that if you were to apply some sort of chemical reaction, you could turn the table salt into its constituent element. You get sodium metal back out, and you can get chlorine gas back out. I wouldn't recommend doing that because chlorine gas is deadly. Table salt is delicious. I don't know why you would turn delicious into deadly, but you do you. So going back to our flowchart. Oh, my flowchart is on the other page, so we'll get that in a second. The qualifying question here is how many types of atoms are in our pure substance? If the answer is 1, then we have an element. If the answer is 2 or more, we have a compound. All right, let's talk about mixtures a little bit. On the board, I have two things that you eat. One of them is delicious, and the other one is disgusting. If you said that ketchup is delicious, you are wrong. I'm sorry. I don't make up the rules. But ketchup does have a quality that the salad dressing on the bottom does not have. And that quality is this. If I were to take samples of these substances, for example, I want this sample, and maybe I want this sample, or maybe I want the sample that's at the bottom of this container. What would you say about all those samples of ketchup? Would you say that there is some difference between them, or would you say that they're all identical? Now, we're going to assume that you've mixed the ketchup bottle really well, like you gave it a good shake. So there's not like that gross liquid at the top or the bottom or whatever. I don't even eat ketchup, so. But if your ketchup is well mixed, all of these portions should be identical. It looks like I have offended some people in the chat. That's okay, ketchup is gross. If you have all identical portions in your sample, we're going to call that sample homogeneous. Homogeneous mixtures are substances whose composition is entirely the same no matter which sample you take. Down here with the salad dressing, however, if I took the top part versus the bottom part, this part up here is mostly oil. This part down here is mostly the good stuff, like all the herbs and the spices, and that's what you want. You don't want to just put oil on your salad because then it just tastes like oil. Because those two are different, even if I shook this, they would eventually settle out and separate. Therefore, no two parts of my solution... I'm reading what you guys are saying, and it's great. No two parts of my solution are going to be the same in my salad dressing, so we're going to call that a heterogeneous mixture. The differences here are that homogeneous mixtures or homogeneous solutions will always be the same no matter what sample you take. Heterogeneous mixtures will not be the same regardless of any samples that we take. In science, generally speaking, one of these is going to be preferable than the other. In the laboratory, which I wish we could go to the laboratory, because then I get to meet you all, you're going to be doing science with multiple trials over multiple experiments. And if you had an experiment that was different every time, I don't know if you could get consistent results out of that. So of these two, homogeneous versus heterogeneous, which one do you think is useful for science? Doing reproducible, repeatable experiments. You can go ahead and put your answers in the chat, and then I will promptly ignore them because I am like 20 seconds ahead of you. But hopefully you wrote down homogeneous. Homogeneous samples are all the same, so we need to use those for science. We talk about heterogeneous solutions because they do exist, and they do have their properties that are important. I know. This is not my first rodeo online, so I know how streaming works. I'm speaking to you from the future. So even if you did say the correct answer, I wouldn't be able to respond to it because I would have already moved on. Now, there is some degree of leeway here. If I ask you if something is homogeneous versus heterogeneous, it sort of depends on how close in you look. Ketchup could be useful if you wanted to like test it for an experiment. For instance, if I asked you, is milk homogeneous or heterogeneous, you might look at it and say, well, it's probably homogeneous. Except what about like the curd or the whey that like tries to separate out at the top? If that's the case, then it becomes heterogeneous. And so that becomes a kind of an issue. Like, where's the fine line that we say, okay, is this heterogeneous or homogeneous? I'm going to try and pick examples that are really obvious. So, for example, an example I like to use a lot is muddy water. If you were a kid and you got to go outside and play in a puddle, and the puddle had like mud and silt and dirt at the bottom of the water, and then the top of the water was clear, you would say that that would be heterogeneous because the stuff at the bottom would be very different than the stuff at the top. If you didn't get to play with muddy water when you were a kid, I'm sorry. You missed out. Here's our completed flowchart. So we've already asked that first question, is there only one substance? Over here on the left, how many types of atoms are in the chemical formula? We're going to differentiate that just purely by the count. So how many types of atoms? If we have one, it's an element, or if we have more than one, it's a compound. And then finally, for our mixture, is everything identical? If it is identical, hey, it's a homogeneous mixture. If it's not identical, it's going to be heterogeneous. All right, that's how we classify matter. Now that I've done it, you get to do it too. Here's a sample of some matter from like the first textbook I ever taught out of, which is why the picture is scanned. I'm going to leave that picture for you to check. It's in your notes, but I'm going to go straight to the examples. So what I want you to do for a few minutes is I want you to categorize each of these entries into one of the four categories. So I'm going to write those categories on the side here so that you remember what they are. So your choices, one for each of these, is going to be... oops, I held the button. I don't know what that did. So we're going to have element. We're going to have compound. We're going to have homogeneous mixture. And then heterogeneous mixture. So you should assign one of those words to each of these choices. For what it's worth, if I list the formula of something, that is the only thing in that container. All right? Good luck. We're all counting on you. Give you 2 minutes to go over the answers. Alright, looks like some people have started putting their answers in. I don't ever really get over to Mukilteo, unfortunately. But I'm always looking for new pizza. Now, one of these choices that I have up here is the trick question. And depending on how much you know about steel, will influence what your answer is. But there is one correct answer, and we're going to talk about that. The reason I put that question up here is because it is difficult, and I want people to sort of like stumble over it and think about it a little bit. And then when I tell you the answer, you'll be like, oh, okay, I didn't know that. Which is fine. Alright, so let me get the pen. Let me get a different color. Let's do purple, because that shows up. What is number 7? We're going to get to it in a second. Alright, so let's start with Red Bull. If you turn the can over of Red Bull, does it say ingredients Red Bull? Turns out the answer is no, which means that it must be some sort of mixture. Now, hopefully, if you are drinking Red Bull that is not, like, I don't know, expired or something, all of the Red Bull will be the same. And therefore, it will be a homogeneous mixture. So the drink itself will be homogeneous, yeah. Now, it does get flat over time, but what will happen to the substance is that it won't, like, dissolve out, like a solid won't precipitate out into the bottom. So the bubbles are part of that phase, but they do escape, and roughly speaking, as far as we can observe and measure, there will be the same number of bubbles throughout the entirety of the Red Bull. So the CO2 is actually dissolved in the water, so we could treat it all as one phase. So, for example, if I were to draw... Actually, let's do this. Do I still have... I don't need this on the screen anymore. So I have this board that I haven't drawn anything on, so let me find where that belongs. Here we go. Alright. Let's see if you can see... Oh, I have a window that popped up in front of it because I'm in Photoshop now. Alright, so, oops, that's the wrong color. Well, that's also the wrong tool. Okay, there we go. So if you had a can of Red Bull like this, and we'll say that you opened it, so we'll just do that. And here was your liquid, and inside the liquid were bubbles. Something like this. As long as there's a roughly the same number of bubbles of CO2 inside the container, we could still call that homogeneous. But if, for example, I had a container that looks sort of like this, like for some reason my Red Bull can like separated into 2 layers, and all the bubbles were in one layer, and all the that was left in the second layer was just like liquid or something. So this would be homogeneous. Ah, that is not the letter E that I was looking for. There you go. That would be heterogeneous. Okay. So something that's dissolved into the aqueous layer, as long as it's the same amount, we will still call it homogeneous. Alright, I gotta get back to the right slide here. There we go. Alright, nail polish remover. I told you that it contains this thing, and only this thing. Uh-oh. I forgot that my tablet does that. If I touch it too many times, it will interpret that as inputs. So if there's only one thing in there, it must be a pure substance. That pure substance contains more than one element, so therefore it is a compound. Let me get this window to the front so I can see your questions again. Alright. We're just talking about pizza, so everything's fine. Poorly mixed gravel. There are these 3 things in it. And the important word here is poorly. On previous slides, I didn't have this P in there for some reason. It was just orly mixed gravel. In either case, it's just a jumble of 3 things. There's no way that everything could be the same. This must be heterogeneous. Next, we have nitrogen gas. Nitrogen gas contains only one element. That's this element. Hopefully you have your periodic table handy so you can look that up. Interestingly, nitrogen gas is actually this formula. And 2. Why are there 2 of them? We'll talk about that in Chapter 4. But regardless, there's still only one element. It's nitrogen, so we call it an element. Even though there are 2 atoms there, they are both the same atom. We'll call it an element. All right. The key word in this next problem is pizza. Pizza is always a mixture. If you are just eating like flour or sugar or something like that, what is wrong with you? That's not pizza. That's something different. That's just sad. That's what that is. But pizza from your favorite parlor is going to be a mixture of ingredients, so it's got to be some sort of mixture. There's no such thing as homogeneous pizza unless you take your pizza and put it in a blender. And again, I defer to my comment about what is wrong with you if you do that. Pizza is always a heterogeneous mixture. In fact, most food is a heterogeneous mixture. Iron metal, this is the only substance that's there, so this is an element, just like the nitrogen above. And then this is the tricky one. How do we make steel? How is steel forged? Well, how do you forge anything, really? Not like forge as in counterfeit or something like that. Like, how do you make it? Well, you make it in a forge. You pour all of the elements into a giant vat. You heat them up so that they are liquid. You then mix them around a lot, and then it cools and it becomes a solid. Now, when you do that, you create a mixture. Yeah, it's a mixture of metals. There you go. So, when you mix all of those metals together when they're molten, you form a mixture, and that mixture cools into a solid. And even though it's a solid, it can still be a mixture. Just like with the poorly mixed gravel up above, that was a heterogeneous mixture. It's just that in doing it this way, since you're mixing it so well that you're allowing it to become the same consistency at the atomic level, you end up getting a heterogeneous mixture. So anything that requires you to mix a bunch of different metals together, the term for this is called an alloy. And all alloys are homogeneous mixtures. So these would be things like brass, electrum, which is that stupid coin in D&D that nobody likes it because it's not a power of 10. Bronze is a homogeneous mixture. Different types of steel are homogeneous mixtures. And you make all of these by making them into a slurry, which is basically a really, really hot mixture of metals, and then you let them cool. So when you hear the word mixture and you hear solution, remember that you don't have to just be a liquid or a gas. Solids also get to apply too. All right, that's how we categorize the different types of matter. Hopefully there are not too many questions that you have. I can quickly answer those, or you can send me an email or put them on the discussion board, and we'll go over them there. What time is it? I still have 20 minutes, so I do want to go over the next section real quick. Talk a little bit about physical and chemical properties, and we'll get into the math stuff on Thursday. So now that we have some understanding of how matter behaves and how we can categorize it, we need to understand what we can do to it. Here are a bunch of actions that I could do to any matter. I'm going to pick that electrum coin, just because somebody mentioned it. If I take an electrum coin, electrum being a mixture of silver and gold, for those of us who didn't know, if I put it in a furnace and it's really hot, it could melt. But if I heat it in the presence of something else, maybe it catches on fire and combusts or reacts or scorches or whatever. Maybe I could put it in water and nothing happens to it, seemingly. Or I could put it in acid and then it might dissolve or might not. And then we could just do other stuff to our matter, such as like we could weigh it, we could measure its volume, you could measure its length, its circumference, you could measure its density, its temperature, things like that. So these are all actions that we can do when interacting with matter. Importantly, on this slide, some of these actions will involve destroying the identity of the matter. You won't destroy the matter, you will destroy its identity. It will no longer be what we said it was at the start. And so we need to figure out what things change the identity of matter and call those a term, which will be a important term that will describe this entire quarter, and which actions do not change its identity, and we'll call it some other term, and then we'll make fun of that class. Okay? So here's our first thing that we want to talk about. First, we got to categorize what a property is. Properties are characteristics that distinguish matter from some other thing. For example, I could say water is a liquid at room temperature. That would distinguish it from anything that isn't a liquid. For example, ice would not be water because it's a solid. Carbon dioxide would not be water because it's a gas. My table would not be water because it's a solid. Let's see here. Is the difference between units and dimensions highly relevant for this class? I'm not sure I understand the second part of your question. Keep typing out. I'm going to keep going, though. These are all just various properties. So basically, any trait that you can assign to something would be a property. Changes are along the same line. These are things that we can do to matter that changes it. For example, you could change a state. You could change something's chemical composition. For example, bread would become moldy if you left it out in a moist environment. If you left iron in a corrosive atmosphere, like there was a lot of oxygen or a lot of water vapor, it would corrode. Those would all be changes. It may be iron, it may not be iron at the end, so on and so forth. Dimensions are time, length, mass, etc. Oh yeah, we're gonna go over all of those probably tomorrow, Thursday, not tomorrow because we don't have a lecture. We're gonna look at various dimensions. We're gonna use length and mass and time a lot in this class. We're going to use very specific SI units for this class. If you've taken an engineering class, you might use imperial units. I will make fun of you for that, but that's okay. I realize engineers work in imperial units. Okay, so properties and changes. We're going to explore these to figure out what stuff changes our matter irreversibly and what stuff doesn't. Here's the rubric that we're going to use. So what I want you to consider, and this is actually going to be a little bit challenging to start because we are starting off chemistry kind of with very little foundation of like what stuff is around us. I want you to consider the chemical formula of the matter before you do something, and then after that something has happened. Now, in some cases, you'll be able to determine, oh, this is obviously changed because its properties are very different. But in some cases, you might not know. What we're going to do is look at the chemical formula being this H2O thing. I'll address that afterward. Any concerns that you have for units after the stream is over. I can stick around in the chat and help you out. So when you're looking at the formula, you're going to have to know what the basic composition is of your substance. For example, water is H2O. If you freeze it, it's still H2O. If you make it steam, it's H2O. Oxygen gas is O2. If you breathe it, it's still O2. If you exhale it, it's still O2. That sort of thing. We're going to try and look for things where it very obviously changes. Let's look at a situation where it very obviously doesn't change. So, for instance, if I have an ice cube, and I let it sit out, the ice cube will melt, and it'll just become a puddle of water. If I look at the formula of my ice cube before and after, then what I note is the following. Oops, I drew a line somewhere. That's okay. So here's my formula for my ice. It's H2O. And here's my formula for my water. It's the same thing. If I have the same formula before and after my process, then what I say is that the transformation that occurred there is a physical transformation in nature. I have not done any chemistry here. All I have done is physics. Physics is boring. So these changes are generally not very exciting. How would I get the water back into ice? Well, I just put it back in the freezer. That's an easy thing to do, right? Physical changes are typically easy to do. That's not to say that physics is easy. I don't want to make fun of physics too much, especially since some of my fellow faculty might be watching these videos. But physical changes are pretty typically reversible, and that reversibility is key for getting our matter back to how it is. But importantly, at the chemical level, the identity of the substance we're working with, the water and the ice in this case, it's still H2O. Those molecules have not changed in any way. If I took a piece of paper here and I tore it into a smaller piece, I just end up with smaller pieces of paper. I don't know the chemical formula of paper, but what I can do is I can say, well, the small piece of paper behaves just like the big piece of paper. I can use the small piece of paper to just write all sorts of stuff on it. I could fold it into a small paper airplane. I can do the same thing with the big piece too. Since they behave identically, I should be able to get the same results, and therefore they must be the same substance. And so that conclusion would lead us to conclude that tearing paper is just a physical change. And it is. It's still paper, even before and after. Even though you don't know the formula, you can infer from its usage that information is handy. Now, there are other things that we can do to paper. So I have a lighter here. And I could take this paper and I could catch it on fire. If I catch the paper... Yeah, I was looking at that tear stencil, and it's very bizarre. I think maybe it's just for like making old paper, or this person just needs to do stencil, because they've used that for too long. If you burn paper, is the result of when you've burned paper the same before and after? I mean, very obviously it's not, because at the end of whatever it is that you get just something in which you have a bunch of black kind of stuff that you could draw with, I guess, like you draw on a wall, you could put it on your fingers. What I'm describing is ashes. Ashes and paper are very obviously different. You can't write on ashes. You can't treat them as the same. Like, you can't fold it into a paper airplane. There's no such thing as an ash airplane. In those cases, the properties are so wildly different than the paper that we have to assume that the formula is different. If you do know something about paper, I can tell you that paper is actually this. Paper is a hydrocarbon made of cellulose. The X is some number. You can write with ashes, but you can't write on the ashes. So, like, you can write on paper, but you can't write with paper. So, therefore, we would conclude that these two things must be different. Some sort of transformation must have happened, in part because of the fire. When that happens, the chemical formula is changed, and what we identify that as a chemical change. So chemical changes involve different substances before and after. You could think of them as kind of like, oh, we have a transformation of matter. Now, depending on what you are looking at, you might mistakenly identify something that is a solid turning into a liquid as a transformation. But importantly, we can turn liquid water back into solid water pretty easily. We just cool it a little bit. It's very hard to turn ashes back into paper. In fact, in order to do that, you basically have to, like, put the ashes in the ground, plant a seed next to it. The tree has to then absorb that matter through the roots, and then it would become a tree again, which we would then cut into paper. There are a ton of processes that are going on there. That is not simple at all. So we would say that this is essentially irreversible. Nothing is truly irreversible, but the degree of effort that we'd have to put in is way higher. If that is true, then what you're looking at is a chemical change. Now, since this is a chemistry course, we're going to be working with chemical changes all the time. Physical properties are common enough, but we want to focus on the chemical changes pretty much exclusively. We're going to be writing those as chemical reactions. We're not actually going to see chemical reactions much this quarter. This right here, as shown. Wow, that was a really good line. I used the mouse for that one. These sorts of statements right here, we're going to see a little bit in lab worksheets, but for the most part, what's important is that the matter on the left side, so here I have some aluminum, I got to have the same amount of aluminum on that side, so here's 4 of them, 2 times 2 is 4, this has 6 oxygen, 3 times 2, this has 2 times 3, everything matches up, so we aren't violating the conservation of mass. But I've taken something that I gotta get a new color here. This and this are not the same. And since they're not the same, what I've done is chemistry. And so that's the gist of what we're trying to get at here. All right, I think I have an example slide on the next page. I do. So I'm going to give you a few minutes to do these. We'll go over the answers, and then we'll call it a day. So I'll give you 2 to 3 minutes to try to categorize these. What I want you to do is tell me, is the action I am taking to do each of them physical or chemical? All right, looks like we've got some answers in the chat. I'm just peeking through the slides ahead. There's actually 2 slides after this I want to go over. So let's do this first. All right, so I'm going to use this water to boil it and make pasta. So I'll throw the pasta in it. Putting the pasta in there isn't the important part. The important part is that the water is boiling. If I am to boil my water, that is going to change it from a liquid to a gas. Since it's still water and I'm not changing its chemical nature, that would be a physical transformation. Down here, grape soda is observed to be purple in color. All I'm doing is looking at it, unless you have like crazy X-ray eyes or something like that, in which case you should see your doctor and get medical attention. You're not going to change the soda by looking at it, so that's also going to be a physical change. I'm just going to write P for physical, actually. For this third one, Alka-Seltzer is dissolved in water. The important language is actually this. Do either of the substances, Alka-Seltzer or water, typically release gas on their own? And the answer is no, they really don't. Water doesn't release gas. If you've ever seen water that's just sort of sitting out and you see those little air bubbles that are forming in it, what's actually in there is air. air and water vapor, but it's not making the gas from the water itself. That must mean that somewhere along the way in the Alka-Seltzer and water bumping into each other, a reaction must have happened to form a gas that comes out, because that gas comes out really quickly. Therefore, chemistry must have occurred in that situation. For number 4, sodium metal is melted. Whenever you melt anything, that's a phase change. Phase changes are physical. Number 5, the gunpowder in a bullet is ignited. When you ignite something, you are typically creating an explosion. But a feature that everything that we ignite has in common is that you can only ignite it once. You can't light it on fire a second time because it's already been used. In that case, what that indicates is that the ignition of the gunpowder has turned the gunpowder into something else that can't be reignited or reused. Therefore, that must be a chemical change. Air is compressed into a scuba tank. Air is the same whether it takes up a bunch of space or a tiny space inside the scuba tank. So compressing something just makes it take up less space. But even if it was a huge space, wow, that box didn't surround it at all. That's okay. Even if it was in this huge space, it's still air. So we're going to call that physical. A woodworker whittles a piece of lumber into a sculpture. If you were just chopping away at the wood, it's still wood. Going to be physical. And then finally, gasoline combusted in a motorcycle engine. Combustion is always a chemical reaction because you are reacting that something. You don't get the gas back after you've used it. You have to go to the gas station and buy more. If we could react the remainder of what was left over from the gasoline reaction, we wouldn't have to keep buying it, and that'd be great. All right, so those are the answers. Real quick, in the last few minutes of the slides, I want to go over intensive and extensive physical properties. Basically, these properties are just a description of how much matter you have and does that affect it. For example, if I measure the temperature of something, it doesn't matter how much water there is in the cup that I'm measuring its temperature. Whether I have 10 milliliters or 100 milliliters, its temperature will be the same. But if I asked you about its volume, the volume would depend on how much matter we have. Properties that do depend on the amount of matter that you have are extensive. I lost my pen. Where's my cursor? There it is. Okay. So an extensive matter property does depend, and an intensive property does not depend. So on the next slide here, I have some examples here. I'm going to just go over these for you. So if I give you more matter, does this value change? Is basically the question I'm asking you. So if I give you more stuff, would you have a bigger volume? And the answer is yes. If I poured you more water, you have a bigger volume. If I poured you more gasoline, would it be any more or less flammable? And the answer is no. It's gasoline. It's just flammable. So something... Oops. Thanks, tablet. So something that does change, this would be extensive. Something that doesn't change would be intensive. If I give you more water, does it boil at a higher or lower boiling point? The answer is, it doesn't. It boils at 100 degrees Celsius, so that's intensive. For mass, if I give you more water, does that change its mass? Of course it does, because that's kind of the whole point of what we've done today. And then state. If I give you more water, will it suddenly become a solid? Gonna go with no on that one. I misspelled intensive. There we go. All right. That does it for lecture number 1. I'm going to hit the button on this to archive the lecture. If you have any questions about anything we've covered today, please stick around in the chat. When I turn off the stream, I think that the chat keeps going. I mean, we could test that. If it doesn't, send me an email or post on the discussion board, and I am more than happy to answer any questions. For what it's worth, some students are in sections OLA and OLB. Some students are in sections OLC. They can't see each other's discussion boards, but if you have questions that you want answered from other students, I will try and push those between the boards. Thanks for watching. I will see everybody on Thursday. Remember, there is no stream tomorrow. Make sure you review the next bit of Chapter 1. We're going to do most of the math on Thursday. We probably won't finish it. Yeah, that's it. thanks again, and I will see you on Thursday. Cheers.